Hi guys, in this video we'll be solving another problem from principal stresses. Here we have a shaft, that is this one, and another attachment is also coming, another link is also coming, and at the end of that one we are applying a force. Here the given force is 10 Newton, and because of this applied load we have to evaluate the stresses, actually the principal stresses at this point A. Point A is coming at this fixed end and this A is at the top outermost element. And here the cross-sectional area is given. From that we need to find the diameter, and this length is given 80 mm and this length is given 100 mm. And first step is we need to find the effect of this force applied at this end on this section. For that we need to transfer this load from this point to this point A. For that, first I will be transferring this applied force from this line to this line, or from this section to this section. I will be drawing an equal and opposite forces at this location, that is of 10 Newton magnitude. That this is also 10 Newton, so that the net effect is 0 and it is equivalent to the original case. But here, out of these two forces drawn, I will be keeping only this force at this section, that is 10 Newton, and these two components, one acting in this direction and the other thing will be creating a couple in this anti-clockwise direction. That means this is in this direction, this is in this direction, and this will be creating an anti-clockwise couple, and that I can represent at this location. So a moment of 10 Newton into 100 mm or 0.1 meter, which is equivalent to 1 Newton meter is acting. And this is actually trying to twist this shaft containing the point A. So this is a torque, and that torque value is 1 Newton meter. I am taking the force is 10 Newton. That is actually too low. And this next thing is we need to again transfer this force from this point to this point A. Then we'll be having the same force I can consider here, and another one I can consider here. Then we'll be having the force of, finally only this force will be remaining, and this will also disappear, and there will be another moment. This will be trying to bend the shaft. That means there will be a bending moment, and that bending moment is given as 10 Newton into distance 80 mm or 0.08 meter, which is equal to 0.8 Newton meter. That means our shaft will be, if I am looking from the side view, this will be the shaft, and this is the point A where it is fixed, and here was the previous case, that is 10 Newton is acting, and I am considering the effect of this 10 will be creating a bending moment. So bending moment value at this section is actually given by this 10 into 0.08. That is what we have evaluated here. So now the shaft is subjected to a torque 1 Newton meter, a bending moment of 0.8 Newton meter, and at the end there will be the transverse force, that is 10 Newton. We usually neglect the effect of this transverse forces because it's the stress created by these transverse forces are too low. So for this case of analysis, we will be taking only the effect of this torque of 1 Newton meter and this bending moment of 0.8 Newton meter. Based on this torque and bending moment, we will be evaluating the principal stresses at this point. So we can consider the element that is at the location of point A, where due to the bending moment we are having the normal stress sigma b. This already we have discussed in the previous problem, sigma b, and also we are having the shear stress that is due to the torque acting, that is tau T, torsional shear stress, and we are having the equation for these two components. So this sigma b is equal to m by I into y, and this can be simplified as 32m divided by pi d cube if we are having a solid shaft. Here we are having a solid shaft whose cross-sectional area we are having, area is equal to 30 mm square. From this we can find the diameter, that is area is equal to pi by 4 t square. From this we can find the diameter as 4 times a divided by divided by pi and the square root. So I'll be evaluating this. I am not having the answers. I can use a calculator and find the values. Hope you can see this calculator. Here first I will be finding the value of this diameter, which is 4 into area 30 divided by pi and the square root. So I will be getting the value of 6.18 mm will be the diameter. So with this I can find the value of the sigma b, which is 32 into bending moment is 1 Newton meter divided by pi into diameter is 6.18 mm or 0.00618 meter whole cube, and this value I can evaluate. Again I will be using the calculator. So bending moment is 32 into 1 divided by pi divided by 0.00618 the whole cube. So this value will be getting us in megapascal, it is 43.15 megapascal. This will be the answer. Next we will be evaluating the effect of this torsional shear stress to T, and here also we can use the expression T by J into R for the maximum R max. Then we are having the simplified equation of 16 T by pi d cube from data book. So here I can substitute the value 16 into torque is 0.8 Newton meter divided by pi into d cube, which is again 0.00618 cube, and this value if I am evaluating, so 16 into 0.8 divided by pi divided by 0.00618 cube, this value we are getting as 17.26 megapascal. So this is 17.26 megapascal. So now we are having the stress components. If I am redrawing the elements and the state of stress, we are having this sigma bending, which is actually the normal stress in the x direction, and the shear stress, that is the in-plane shear stress. Here we are having sigma x, which is due to the sigma bending, which is 43.15 megapascal, and there is no normal stress in the y direction, so sigma y is equal to 0, and tau xy is due to the torsional shear, which is 17.26 megapascal. So for this stress components we can use the principal stress equation for evaluating the principal stresses and maximum shear stress at this point A. We are evaluating the stress at this point A, and this is the state of stress. This is the state of stress for that point. So next we will be evaluating the principal stresses. So here we are having the expression for evaluating the principal stresses. Already we have seen in many problems. So here we will be substituting the values of sigma x, sigma y is 0, and this tau xy. Here also we can use the calculator. Here 43.15 divided by 2 square plus the shear stress is 17.26 plus 17.26 square, and the square root of this one is 27. So plus or this is plus or minus 27.63 megapascal, and 43.15 divided by 2, this is 21.575. so you can evaluate this. Plus 27.63 is 49.21, approximately 21 megapascal, and the other one will be 21.575 minus 27.63, which is minus 6.06 megapascal. So here we have obtained this as the maximum principal stress sigma 1, and this is the minimum principal stress sigma 2, and the maximum shear stress at this point is sigma 1 minus sigma 2 divided by 2, which is 49.21 minus which is plus 6.06 divided by 2. The value will be 55.27 divided by 2, around 27.77 megapascal. So this is the final answer. We have seen the procedure for evaluating the principal stresses and maximum shear stress for the given problem. So hope you understood, and thanks for watching.